University of Ceará, who will tell us about min-max widths compared to other geometric invariants.
Okay, can you hear me? Yeah. Yeah. So thank you very much, Vinicius. So maybe I would like to thank the organization and staff for putting together this meeting. It's very nice. So, and also thank you for the opportunity for me to speak here, for the invitation. So I'm going to, so far this week we had many very nice talks and introductions to systolic and diastolic type results. So I'll still take a moment to make a brief overview, more guided towards the results I want to talk about. But my title is on min-max widths and comparison with some other invariants. So usually it's going to be diastolic type inequalities. So let me start just reminding what kind of invariants are these. So instead of just start by defining in some specific situation, let me just tell you that usually these kinds of min-max invariants that I'm going to consider, they are associated to existence results of closed geodesics or minimal hypersurfaces. And so this implies that they are related to some special values of, special critical values of the volume functional of codimension 1 objects. And they are related to constructions associated to some non-trivial topology of the space of codimension 1 objects. Right. So here I summarize some results just to remember that we have many examples. Of course, the results are not, so the results that I'm stating are not proven by all those groups. I'm mentioning here, I'm trying to mention groups that had results related to those things. So the first started, maybe the first person to work on this, to have a result on the existence of one closed geodesic in any two spheres Birkhoff, but we have many other progress after that. So in the end, we have that every two sphere has infinitely many closed geodesics. And we also saw in other talks this week the analog in high dimensions. So this result here that says that every closed Riemannian manifold of dimension between 3 and 7, you also have infinitely many embedded minimal hypersurfaces. So the theory is rich in examples, and also we saw a deep connection with the theory of eigenvalues of Laplace operator. And I will come back to this in a second. Let me just explain very briefly with this picture that I think at least the picture on the left appeared maybe yesterday in Andre's talk. So I'm trying to make a picture here of the space of hypersurfaces, and I'm considering a path of hypersurfaces starting and ending. So this yellow path is a path that starts and ends in this hypersurface here indicated by the red point, the hypersurface of zero volume, and this path detects some non-trivial topology in this space of hypersurfaces. And on the right, I have what would be this path in the ambient. So the ambient here would be, so here I'm using a two-dimensional object, so the ambient is two-dimensional, and we have here a path of curves, of closed curves. So these curves start and end with points which are curves of zero length, right? And they are detecting this non-trivial topology in the space of closed curves. So this is the parallel, the yellow closed curves here on the right, they are just points in this yellow curve here on the left. So we saw that it's very important for the theory for the existence of infinitely many minimal hypersurfaces, for example, that there is this analog of the Weyl law in the case of the volume spectrum. So we have a sequence of min-max widths which behave in this way compared to the parameter p. So you do the min-max in the class of p sweepouts, and you get a different numbers omega p, and they have this very nice behavior. So in this setting, as mentioned in other talks, this was conjectured by Gromov and proved by Liakumovich, Marquez, and Neves. And this and other things that we already saw make a deep connection of this theory to the theory of Laplace eigenvalues, right? Extremizing Laplace eigenvalues. So maybe motivated by this, we have some other geometric inequalities relating this invariant and other geometric quantities. For example, so at this point, I'm going to have some simplified versions of results. So this is a result proved by Fernando and André, in which they have this inequality. So this capital W is the width in the class of when you do the Moss theory for the space of surfaces that are spheres. But if you have this restriction on the curvature positive Ricci, then it coincides with the width that we were talking about before, the Green-Pitts width. So they proved that the width multiplied by the infimum of the scalar curvature of a metric in S3 is bounded by 24 pi, and this is an optimal inequality. The equality holds if and only if the metric is round, right? So this is maybe the first result that relates the area of some, because this width, as I mentioned, is related to the area of a minimal sphere. So maybe this is the first result relating, the rigidity result relating the area of a minimal sphere in the presence of a scalar curvature condition for a sphere which is not stable, right? There were results before that on the rigidity of minimizing and stable spheres, but here it's an index 1 object. And it was a question at the time whether or not this condition on the Ricci curvature could be removed, and actually, so you would have a statement only on the scalar curvature, but actually that's not possible. So it was part of my PhD thesis here at IMPA that you cannot drop this condition. Actually, even this product is not going to be bounded. You can find examples with positive scalar curvature using Gromov laws on construction, on which this product here is going to blow up. Right? So it's going to increase to infinity. Okay. So another inequality that I obtained, so this one I obtained with Lucas maybe 5 years ago or so. So we also motivated by this connection with eigenvalues of the Laplace operator, we try to compare this number, the same number that was in the other inequalities, to the volume of the ambient space. And we noticed that you cannot do this in general because this quotient, if you quotient the width by the volume to this right power, so it's scale invariant, it's not bounded for all metrics on S3. For example, if you look at Bezier spheres, it's not going to be bounded. But if you restrict yourself to metrics in the conformal class of the canonical metric, then we have this optimal inequality and rigidity, right? The equality. So this number that you get here is exactly the quotient of the width divided by the the right power of the volume in the case of the round sphere. So equality holds if and only if you are round. And of course, it's important to compare this to other results that appeared in the conference before the beginning of the week, showing that there are some similar things and some different things in 2 dimensions. So for the round 2 sphere, you know that because if you look at positive Gauss curvature in the 2 sphere, the systole is going to coincide with this width, and you know that the round metric in the 2 sphere is not optimal. There's this the Calabi-Croak metric, which is also going to be relevant later in the talk. So I'm not going to spend time now discussing this. But we know after results of Alberto and Humberto, Pedro and Braham that it's a local maximizer of the systole and also the width in this case, right? So also related to this result, with Lucas, we obtained a necessary condition for a metric on S3 to be a local maximum of this normalized width in the conformal class. So namely, the result is the following. So very roughly here, it says that if the metric is maximizing, even locally, then you have many minimal 2 spheres of index 1 whose area equals the width. Right? You have an equidistributed sequence of such objects. Right? So you can also do a similar, there is in the literature, there is a similar characterization if you study a relative width, but it looks like there are no standard natural examples to consider in that case, as the example that we have here for the round metric, of course. So we also expect other objects such as Zoll metrics to be optimal in their conformal class and satisfy some inequality like this. But so far, we only know that this is true. The inequality is true in this, for this example of the round metric. Right? But motivated by this analog with the relative case, we consider like a lower dimensional width that can be compared to some invariant of the boundary, something like this. And this is related to this other work that I want to discuss now. I'm going to be brief on this as well and focus on something similar later in a few slides. But maybe this is a point to see if there are any questions so far. Okay, so if there are no questions, so in the next few slides, I'm going to talk about joint work with Lucas and Rone, who is also here. So in this case, we consider widths of curves embedded in some Riemannian manifold. So here we have 2 pictures that could be the case. So it doesn't matter if the curve is embedded in something, in a surface. It could be in some higher dimensional space. So gamma is just an embedded curve. And we consider the Moss theory for the following function. So we consider the distance function on pairs of points. So actually is sets of points in this curve of at most 2 points. So it's either 1 or 2 points. Right? So there's this set here that has a topology of the Möbius band. So, and the boundary of this Möbius band is exactly the trivial pairs. So those are the pairs made of a single point. The 2 points, they coincide. And of course, the distance is 0 on this boundary. And you have the maximum is just the diameter. It's the extrinsic diameter in the case the curve. So in all cases that are relevant, right? So it's the diameter of gamma in the ambient that it's embedded. So since this is the Möbius band, it's natural to try to find another critical point. So, and this is what we do. We consider the non-trivial topology of the Möbius band in the following way. So we construct paths in this space of pairs in the following way. Right. So we're going to, following the general terminology, we call a sweep out of gamma is just a continuous map defined here on the unit interval in the space of pairs in such a way that so we have actually two continuous paths. So phi of t is 2 points, pt and qt, in such a way that they start and end at the same point. So p0 and q0 are equal, and also at the end. And if you follow through this path of pairs, for each time you have an arc of the curve gamma that we call ct that goes increases continuously from just a point to the whole curve. So like in this picture here. So here C0 just coincides with the point. So at time t equals 1/3, maybe this curve C 1/3 is this arc here, and at time 2/3 it's this bigger arc, and then it closes on the other side. Right. So these are sweep outs. So it's paths defined in this way, and you do the usual. You construct the usual min-max invariant. Now for the distance, for each path, for each sweep out, you maximize the distance, and then you take the infimum over all sweep outs, and you hope to show that this is a critical value of the distance function, and to get some results after that, afterwards, right? So let me show you here an example, because so maybe it's natural if you think of this curve gamma as the following. So if gamma is, for example, the boundary of some convex region, then one could expect to find a critical pair realizing this width made of this point P and Q in such a way that the distance between them is just the length of a minimizing geodesic, which is also orthogonal at both points on the boundary. So this can happen, but there are other situations. There is another situation which is also relevant, which is the following. So it's the situation that happens here, for example, for this curve in this elongated ellipsoid. It's a very simple example. You take this elongated ellipsoid, and so this red curve is what you get. It's a horizontal cut. It's a horizontal circle, but you cut a little bit above the equator. So if you pick 2 points which are, say that this ellipsoid is an ellipsoid of rotational ellipsoid, you take 2 points here and here, which are symmetric with respect to the z-axis, the axis of revolution. Then there are 2 minimizing geodesics realizing the distance between them, gamma 1 and gamma 2. And this is the same if you pick any other pair. It could be any other pair in this red curve, any point in this curve, and the symmetric one. So any point is in a pair like this. Right? So of course, if you do if you take any sweep out of this red curve by pairs, you're always going to have the sweep out always going to have a pair of points like this. So, and this is actually the diameter. So it's the maximum of the function. So in this example, the length of these 2 curves, which are the distance between the 2 points, the end points, this is the width. Right? So this is the width, and it's not realized by a free boundary minimizing geodesic. Okay? So a few remarks on this work. So of course, so we have a slightly generalization of the notion of regular and critical points of the one introduced by Grove and Shiohama. So in that case, they fix a point and use the distance function from that fixed point. So here we have the 2 points varying, but there is a similar notion. And we showed that this number is actually, in general, a critical value of the distance. And we study this inequality, which is easy because, of course, this critical value is bounded by the maximum of the function, but actually the equality case in this inequality is very interesting. So we find it very interesting. For example, we showed that the curves reaching this equality have the following property that, so I'm assuming now that a curve, so it's like a Zoll-type phenomenon for these objects. So for every point in gamma, if gamma satisfies equality here, every point you have another point in the curve which is diametrically distant. Right? Any point has another one which is diametrically opposite. And we also show a converse. So this is actually, so this direction that I'm claiming here, it's easy. The other direction is a little bit more involved. Another interesting thing that we did in this work is that we obtained, as in the last dot here, we obtained some existence theorems. It's a dichotomy theorem, basically saying that under some natural assumptions, in the case that is in the blackboard here, so it's similar to this, like a curve bounding a convex domain of say, non-negative Gauss curvature, or it could be just a curve bounding a region on which you don't have a free boundary stable geodesics, then we can show that either you have a free boundary geodesic which is minimizing as well, or you have a situation similar to the one in the ellipsoid, where you have two, exactly two, in that configuration. Right? Okay. So do you have any questions? So I didn't give a lot of details on the previous work because, so first, I want to focus on this, and also the results in the other work with Lucas and René. They are some of them are similar to the ones that I'm going to mention now. This is so from here on, it's going to be on a joint work with my PhD student in Fortaleza, Idalina Ribeiro. And basically what we try to do here is to see what happens if you consider the distance function now for pairs of points in a sphere, right? So the related question to the thing that I drew on the board is, of course you know that every two-sphere has a closed geodesic, but you not always expect that this closed geodesic is made of two halves which are minimizing. It doesn't have to be like that, even if you pick the simplest one, right? Maybe. So you know there are closed ones, but you can ask yourself, if you do the min-max for the distance function and for pairs of points in the sphere, is it possible? It's possible that you get this closed geodesic with two halves which are minimizing, but what else can happen, right? This is the motivation in this work here. One of the motivations. So Now we consider sigma is an embedded to a sphere, but also in this case, different from the other one for curves, even the intrinsic case is relevant, because you can do, in the other case, if you just take the curve, the intrinsic thing would be measuring distances in the curve, so that's not interesting, right? But here, measuring distance in the surface is already interesting. So, but again, we consider the space of pairs of points or sets of at most 2 points. So this is capital P sigma is the set of pairs, and this has the topology of CP2. It's homeomorphic to CP2, and in order to define what are the sweep outs that we consider, we construct the following path, the following map, which is going to be our, say, the standard sweep out, which is simply the sweep out that associates to each point in the sphere the pair, which is this point, and a fixed point, a point which is, so we fix x0 in sigma, and for any other point in the sphere you take, so here you can, we are dropping the notation on the, there is an embedding here from S2 to sigma, right? So this would be the pair made of x0 and the image of x via this embedding of S2, right? And for us, the sweep outs are going to be maps from S2 to the space of pairs of points, which are made of two maps, two continuous maps from S2 to sigma, phi 1 and phi 2, and which are also homotopic to this standard sweep out, right? And we can show that the sweep outs that we define, they are not homotopic to a trivial map, a map that associates to each point on S2 a trivial pair. Right? So this is showing that if you define your natural min-max width, it's going to be positive. So this number, right? If you take the min-max, the associated min-max number, it's going to be positive. So for each sweep out, you maximize the distance between among all pairs of points in the sweep out, and then you take the infimum over all sweep outs. This is going to be positive. Otherwise, this sweep out would have phi 1 equals phi 2 always, and these two are not. So any sweep out of this form is not homotopic to phi 0. So it's not a true sweep out. Okay. Okay, so yeah, so of course now it's naturally to state this basic result, saying that under the natural extension of what you should understand as a critical point or a regular point, we can show that this min-max number is actually a strictly positive critical value of the distance. Some basic examples here. So in the case of the round to a sphere, this width is exactly half of the length of a great circle, of course. So it's one of the situations, so in this basic situation, it happens that what you get here is the same as you get a closed geodesic, right? But it's half because, so the number that we have here is half of the length of this closed geodesic. But the same thing doesn't happen, for example, if you consider positively curved spheres near the Calabi-Croke example, when you glue together two triangles. So I'll try to show this after we have some other results, which make this example more simpler to explain why this happens. So in particular, we see that we are dealing with an invariant which is it's different from like a systole or like the diastole. The diastole that you get when you do min-max with the length functional. So that's the comment. And even in the case that sigma is embedded in some space, you even have more examples. It's easier to get examples on which these two things, the free boundary geodesic does not coincide with the thing that you get here. So it's an example similar to the one with the ellipsoid, the elongated ellipsoid. Okay. So in order to try to be a little bit more precise on the constructions that we make, the main objects that come up here in this work, I want to properly define the notion of critical points and regular points of the distance function. So we start with the notion of a regular point. So we fix a pair of points in sigma, and we say it's a regular point if there exists, so a regular point if there exist two vectors in the tangent spaces of x and y, the tangent spaces of sigma, with the following property, that every minimizing geodesic connecting these 2 points, if you move this geodesic in the direction of any vector field which coincides with W1 and W2 at the endpoints, then the length is going to decrease in first order. So this is regular. It means that for other pairs of points near x and y, you can decrease the distance because you're decreasing the length of the minimizing geodesics. You can decrease the length in a given direction. So this is the notion of a regular point. So it's a regular pair of points. So otherwise, you say that it's a critical point. So a critical point is a pair of points in such a way that there is no way to decrease the length of all minimizing geodesics in the same direction in first order. So here we have a characterization. We have a characterization in terms of the structure of minimizing geodesics, which simplifies a lot our life, which is the following. So actually we start with it could be an example. This could be an example. If you take k curves, right? If k curves are simultaneously stationary, in the sense, so what's here in the parentheses is the definition of what I mean by simultaneously stationary. So it means that there is no way to decrease. So here I have in other words, but k minimizing geodesics connecting x and y, they are simultaneously stationary if there is no direction that decreases in first order the length of all of them. So that's the same if you use just the first variation formula. This gives you the following. It gives you that the speed of this geodesic at both endpoints, you can combine them in a convex combination with the same coefficients at both points to make them vanish with the same coefficients. So this is simultaneously stationary. And you have, if you have k curves satisfying this condition, then the 2 points are going to be critical because there is no way to. So it's just plugging in the first variation formula. And since we have this characterization of simultaneously stationary curves, minimizing geodesics, in terms of a convex combinations here of these vectors. So here the orthogonal projections of the speed vectors in the tangent space of sigma, because here we also considering the embedded case. So because you have this convex combination configuration characterization here for the set of simultaneously stationary, then you can also show that any critical point is of this form. any critical point actually can be represented by a set of at most 5 simultaneously stationary minimizing geodesics. And this 5 comes from a theorem of Cara-Teodori, which says, so here we have, if you look at the pairs, so let me just write, I didn't write. If you just pair, say, gamma I prime 0, gamma I prime A, so this is in this 4-dimensional vector space. So this is the tangential part. So you have even if you look, you don't need this I here. For all minimizing geodesics, so you have a compact set of minimizing geodesics connecting these 2 points that are fixed. And for each geodesic, you can associate this vector here in this 4-dimensional, in this R4 here. And if this is if there's a convex combination if 0 is in the convex hull of the set, then it's going to be a convex combination of at most 5 points in the set, right? So that's the characterization in terms of simultaneously stationary minimizing geodesics. For example, if you have a set with only 1 simultaneously stationary geodesic, then you must be in the embedded case, and this must be a free boundary geodesic, which is also minimizing. And if you have exactly 2, then you must be in the intrinsic case. And these 2, they must be, if you put these 2 simultaneously stationary geodesics together, then they make a closed geodesic. Okay. So the first application is the following. So far we haven't considered any restrictions on the metric on S2 or on the ambient. So here we have a result on which we consider only the intrinsic case, and there is an extra assumption on the geometry, which is the following. You consider 2 sphere which does not contain stable closed geodesics. Then we show that only 2 things can happen. Either this width that we consider is realized by the length of half of the length of a closed geodesic, which is made of 2 minimizing geodesics, or you have 3 simultaneously stationary, or a set of 3 simultaneously stationary minimizing geodesics. So what I'm saying is that you can rule out, in this case, under this extra assumption, you can rule out the cases of 4 and 5 simultaneously stationary geodesics, minimizing geodesics. Okay. So also related to this inequality, comparing this width with the diameter, we also have a similar characterization in terms of spheres realizing. So this is general again. You consider either the intrinsic or the embedded case. So an embedded 2 sphere, when I say embedded, could even be just the ambient could be sigma again. Then we have this characterization again of metrics realizing this equality. So actually we break this into 2 parts. So if you have equality, if the width equals the diameter, then for each x, that is an y, which is diametrically distant. But the converse, we don't have. It's similar to the situation that we have in the case of curves. We actually need to assume that there is a continuous map which associates for each point another point which is diametrically distant to show that equality occurs in the inequality. But this is in general for embedded spheres, but this assumption can be dropped, and you have if and only if in the intrinsic case. There's a moreover part here. So in the intrinsic case, the width coincides with the diameter if and only if, for each point on the surface, you have one which is diametrically distant. So this is because in this particular case, we can show that any point belongs to this, is similar to what happened for curves. For each point x, it belongs to at most one critical pair, which is not trivial, which is not just the point itself. Okay. So, but using the uniqueness, you get the continuous map that we ask in part 2. And then you can apply part 2. So another application, I'm not going into details here because I want to go back and talk about constructions. And, but here we have another application also related to this inequality. So this inequality that I just showed you, this inequality shows that surfaces that have a width equal to diameter, these two critical values, when they coincide, then in the embedded case, this is a property which is similar, exactly the same as a property that holds for surfaces in R3 of constant width in the classical sense. For the width, which is defined as the least possible distance between two parallel planes on which you can put the surface together, inside, right? You can put the surface inside. So then it's natural to think of this condition of this width being equal to the diameter as a generalization to Riemannian setting of this condition of surfaces of constant width, this classical notion. And one result, so there are many examples of surfaces of constant width in R3. And for example, if you take like a roller triangle and you rotate, then you get an example. So, despite that, if you force the surface to be centrally symmetric, then it must be a round sphere. So this is an example of a result in the classical theory of surfaces of constant width that we can generalize for the Riemannian setting the following way. So we have here some conditions. So we have you can think that we have many hypotheses, but actually 3 of those. So the hypothesis 3 is asking for the symmetry, but 1, 2, and 4, they all hold locally. So the result says that you have something similar if you assume that you have like a sphere which bounds a small region in a Riemannian Riemannian surface, right? Or actually a Riemannian 3 manifold. If you have a, so let me read this with you. So you have a 3-dimensional object, three-dimensional. Omega is a subset, is a region, and diffeomorphic to a 3-ball. And you suppose some conditions that you see easily that these conditions hold locally. So for every 2 points in omega, there is a unique minimizing geodesic connecting them. Every geodesic emanating from a point in omega, it's going to leave omega at some point. So, and point 4 says that any non-minimizing geodesic joining points of omega, maybe there is a geodesic that goes out and comes back to omega, but these geodesics, I'm assuming that they are longer than the diameter. So these are properties that hold locally. And if you assume these things, so if you assume that omega is in a small neighborhood of a point, for example, and you have an isometric involution without boundary fixed points like central symmetry, and the width coincides with the diameter, then this region must be a ball, so a geodesic ball, anametric ball. Right? Okay? So I also wanted to mention there's a comparison with the Almegren-Pitts width in the case of of positive curvature. So in this setting, Calabi and Cow, they proved that the first width in Almgren-Pitts theory is realized by a closed simple geodesic. And in this setting, we can show that our width is bounded by half of that. Okay, it's always bounded by half of that. So if it happens, the situation with 3 minimizing geodesics, then actually you have a strict inequality. So you see that if equality holds, then there must be 2 distinct minimizing geodesics such that the union is an index 1 closed geodesic. Okay. Okay, so in the remaining time that I have, I'm going to go back to some results into the proof of this dichotomy result, basically. So the result that says that either, so in the situation in which you have, you consider that this twist sphere doesn't have a stable closed geodesics, then either the width is realized by a pair connected by 2 minimizing 2 simultaneously stationary geodesics, or 3. Okay, so this is so this theorem here is representing one of the constructions that we have to do of sweep outs. So it says the following. So it says that if you assume the hypothesis that I mentioned, then the width is actually the lowest strictly positive critical value of the distance. So this is just repeating the statement. You have 2 or 3. So the main idea, the key idea is the following. If you have 3 minimizing geodesics connecting these 2 points, x and y, which realize the width, and they satisfy that the angles of the speed vectors at the origin, say at the origin of, at the tangent space of x, they all make angles which are at most pi, and the same thing at y, at the tangent space at y, then this set must be simultaneously stationary, because otherwise you can construct a sweep out which would be better. Right. So the idea is basically the following. So let me try to sketch the construction. So you have the sphere. So I'm assuming, so let me say that this is x and this is y. And you have 3 curves, one here, gamma 1. Let's say this curve on the board here, on the plane of the board is gamma 2, and gamma 3 is maybe on the back. Right. So what we do in this, so let me just say gamma 3 is on the back. So what we do is, instead of constructing directly the sweep out by pairs of points, we construct sweep outs by curves with bounded length, so with lengths bounded by 2 times the distance between x and y. Remember that each gamma I here is minimizing, so the lengths are all equal to the distance between x and y. So you can, if these angles here are convex, then you can use the Birkhoff construction to, if you are under this assumption on existence of no stable closed geodesics, then if you run Birkhoff argument, the length decreasing argument, then these curves are going to shrink to a point. So the idea is to run this Birkhoff curve shortening procedure in each of these 3 regions. So for each one, what you get is a sequence of curves of decreasing length. All lengths are bounded by 2 times the distance between x and y. So for each one of these regions, it's like you have a map from a disk to disk to this region, mapping like the circles to these curves of controlled length, and this point is just the final point of the Birkhoff process, right? So now what you do is you have 3 maps of disks like this, and you combine them because on the boundary, they are just parametrizing the curves gamma 1 and gamma 2. So if you do the exact same construction on the other 2 regions, you have a similar picture. So now, in order to construct, so we still have a sequence, like maps, which give you curves. But now what you want to do is, for each such curve, you are going to have a marked point, which could be, for example, the formation of point x from x. So we have a path from x to here, to this point here, right? So we have now maps from the 2 disks to the space of pairs of points. So for each point, I'm going to map this point on the disk to a corresponding point on the curve, and the point on the curve corresponding, say, to this fixed point here of the intersection of the circle with this fixed axis here. So what happens is that the distance between the images of these 2 points is going to be strictly less than the distance between x and y, because this curve has length less than 2 times the distance between x and y. So you have the length to control the distance. So and now you have these maps from disks to pairs of points, and you glue them together, the 3 of them together. You have a sweep out. So this shows that if you have these 3 curves in the configuration in such a way that these angles are all convex, then the width is going to be at most the distance between x and y. But if you assume that these 3 curves are not simultaneously stationary, then you can you can deform a bit the middle curves to decrease length strictly. And when you decrease length, the estimate on the distances improves, and you get a better sweep out, showing that in this situation where the curves have this angle property, the convex angle properties, the 3 curves have the convex angle properties, then you would get a better sweep out than the one realizing the width, because we picked x and y realizing the width, okay? And then you would get a contradiction. But we still need to show that we have 3 curves in this situation. We didn't prove that yet. What we know so far is that you have a set of up to 5 simultaneously stationary minimizing geodesics, okay? So what we are showing is basically that if you have 3, in this situation, which is weaker than simultaneously stationary, then they must be simultaneously stationary immediately, right? So what we do is, when you have a 4 or 5, then actually you can get in the situation. You cannot remove one, like when you have a 4 simultaneously stationary, you cannot remove one to get 3 simultaneously stationary, but you can remove one to get in this situation with the convex angles, and then you use this argument to show that they must be simultaneously stationary, okay? So this is just explaining what I made in the picture. And here is it's like a convex geometry lemma that allows us to roll out, to go from 4 simultaneously stationary to 3. I like this lemma. We have a proof in the article, which I like, but I don't like from another perspective, because it's quite long. I think there should be another simpler proof, more elegant proof. And but it's very simple. For example, you can think of the following. So I'm going to make a picture to illustrate. It's better. So you have I have 2 sets of 4 vectors in R2. So the first one, they're all unit vectors. So I have a V1, V2, V3, and V4. And they appear here in the unit circle in this order, right, in the counterclockwise direction, or maybe there's different, but what matters is that you have another set, W1 to W4, which appear here in the unit circle in the reverse order. In such a way that the origin is a convex combination of both sets with the same coefficients. Right? So what we prove, what you want is to show that there is a set of indices, say 1, 2, 3, in such a way, so here would be maybe 1, 2, 4. So if you pick W1, 2, and 4, V1, 2, and 4, you see that the origin is a convex combination of these three sets, these two sets, V1, 2, and 4, W1, 2, and 4. So it's the same indices. Okay, so you have 4. The origin is a convex combination of both sets with the same coefficients. Then there is a set of 3 indices in such a way that the origin belongs to two triangles with the same indices in both pictures. So, so we use that. That's one important step into the proof of ruling out 4 and 5 simultaneously stationary minimizing geodesics. And finally, I want to go back and mention the situation of the Calabi-Croak example. This is, again, it's a metric on the tree-sphere with 3 conical singularities, but it can be approximated by positively curved metrics on S2. So what you do is you glue together two equilateral triangles, say they have unit length, sides of unit length. So the corollary that I want to show, the last thing I want to show is that in this situation, the width is realized by, the width cannot be realized by a set of 2 simultaneously stationary minimizing geodesic, right? So it's a situation in which we know for sure that you don't get half of the width of closed geodesics. So otherwise, if you have a sequence of metrics in this situation converging to the Calabi-Croak sphere, then you would have a sequence of closed geodesics in these metrics GM converging to a closed geodesic in the Calabi-Croak sphere. And we know that in the Calabi-Croak sphere, the closed geodesics, they all, if you take the length of side of the triangle to be 1, then all closed geodesics, so through any point there are exactly 3 closed geodesics passing. And otherwise the point is just the vertices. So, but the length is going to be 2 times the height of this triangle. So that's square root of 3. And then the width would be at least this number, because it's half of the length, right? It's half of the length. On the other hand, there is a very simple sweep out which is better than that, which is the sweep out that you consider, that you get doing the following. You fix x0 to denote the center of one of these 2 triangles, and the sweep out is just a standard one with respect to this point. You take any point in the sphere in any one of the 2 triangles, and you map x to the pair x and x0. And the maximum distance here is square root of 3 divided by 3, which is strictly lower than the estimate you get using closed geodesics, right? So it's simple. To see this maximum is simple. So this is x0. So the maximum distance, so this is the other triangle, which is already glued together in the side here. So the maximum distance is exactly this, the length of this segment here. Okay, so I believe this is my last slide. Thank you very much.
Are there any questions?